the intent is to tell you what classes you might want to take to get a well-rounded education.
Yeah.
But it's not meant in the same way. But you know, it's practical. Doing good grad. I mean, the current problems at IFA started long before COVID. There are some post-COVID things that, that really haven't quite cleared up.
And then I'm guessing there's,
Mute yourself. Hey, how's it going?
Yeah. Yeah. Yeah, it's very well. Just most of the stuff is happening in this program, so you'll work on. I think it's also good because you'll get less distracting if you do like this ellipse, so wait like it's. Yeah, there's only because of those. Yeah. I like I have
I'll be like really
people like
so we'll just wait.
just talking about.
I figured that would
not already
happen, yeah.
practicing,
They're like,
so, like if you are.
Yeah.
if you're
I don't know how many
really
times I
focused,
did that, whatever.
like
Just get on all of it.
Yeah, it's very quiet.
Yeah. And now with the summer almost being over, it's not spot. But it's even new. But is it?
I will say that I have been pretty good with the best in there, but I opening the window,
Yeah,
since it's cool now.
Yeah.
I open the window.
I remember you mentioned. Yeah.
Fortunately.
There are no neighborhoods actually that, there are no.
Yeah.
Just.
Right, thanks everyone for coming. It's great to have JJ here for today and a little bit of tomorrow. JJ is a theoretical astronomer. Yeah, kind of hydrodynamics, disks, planets, systems, how do we form them in the ways that we see them? He's just moved to Penn State, transferred his 51 Peg fellowship from Berkeley, and is now gonna start at Penn State as faculty in about a year. So I'm excited to hear about your talk.
Thanks so much for the invitation. Yeah, so like I said, I'm a theorist. I like to try and think about the ways in which different planetary systems form, in particular the orbits that they have, what sets their architectures. So the reason why I do this is I try and place our own solar system in context. So with the TESS and Kepler missions, we now know that there are many exoplanetary systems. When we compare it to our own solar system, have much more quiescent orbits. Orbits are much more coplanar, circular. And we know by looking at protoplanetary disks, where we now actually see these types of planetary systems forming, that the disks itself is nearly circular and coplanar itself. It all kind of fits in. We know this because for these systems where we look at the dust, we can trace the rings of dust and we can measure their ellipticity as well as their inclination. We know that the rings of dust are also nearly circular and coplanar. So many systems are much more dynamically quiet than our own solar system, but there are a large number of systems which have a much more dynamically active past. So some planetary systems have large inclinations between the orbits of the planets, like Kepler 693 here. 50-degree inclinations up, and there are a growing number of protoplanetary disks which are inclined as well. I'm showing here HD 142527, transition disk, protoplanetary disk with a big hole in it. And if you look at it in scattered light, you have these two diametrically opposed shadows. And these shadows are cast by an inner disk, which is highly inclined with respect to the outer disk. And that's because starlight is hitting the nodes of this highly inclined inner disk. So some planetary systems, very quiet, others have really large inclinations. And what my research emphasizes is that the key to understanding this diversity of exoplanetary systems lies in fluid dynamical interactions. And we're going to talk about today is how different fluid interactions from when the planets are forming in their natal protoplanetary disk to after the disk dissipates and you just have a planet interacting with its fluid host star, all of these different interactions are really the key to understanding how these exoplanets architectures are sculpted. Okay, so we're going to start off by thinking about protoplanetary disks. In particular, we're going to think about disks in binary systems because they're very common. Around half of sun-like stars are in binaries. If you look at binaries in star-forming region, an appreciable fraction of them have disks. And what we're going to do is we're going to start off by thinking about circumbinary disks because the interactions here are very strong. These disks are often tidally truncated by the inner binary. And so these interactions play a really large role in setting the architectures of these systems. Okay. So you look at circumbinary disks, and we know that most of these systems have the disk, as well as when the disk dissipates and you're left with a planet. Most of them are nearly aligned with the binary orbital plane. And this has a natural explanation, right? These things form from the same giant molecular cloud that's rotating. After the cloud cools, you form an aligned system. However, there are a number of disks which have large inclinations with respect to the inner binary. And one explanation for this is you just have turbulence, right? So turbulence is really good at scrambling inclinations. The turbulence sets the disk to be at a higher inclination with respect to the binary. But what this doesn't really explain is some of these systems, especially when the inner binary is pretty eccentric, have very peculiar architectures. So I'm showing right here this debris disk 99 Hercules, where if you look at the orbits of the dust particles, they have orbit normals pointing in the direction of pericenter of the inner binary. And they're inclined with the binary's orbital plane by 90 degrees. If you're going to explain this with turbulence, that's quite literally like flipping a coin and having it land on its edge, because this is actually the maximum energy state of the system. And so what I'm going to talk about today is that these systems weren't born like this. A fluid dynamical process actually sculpted the system to end up in this very peculiar architecture. What I'm showing right here are these SPH simulations, which show if you start a fluid protoplanetary disk around an eccentric binary, what's going to happen is this disk is going to grow its inclination and evolve into what we're going to call this polar line states, where the disk is at a 90-degree inclination with the binary, and the disk orbit normal is pointing in the direction of the binary's pericenter. But we're not only going to show that these fluid, in particular, these viscous torques acting between the disk and the inner binary are what causes this. We're also going to show that this process is also what causes most circumplanetary disks to have nearly aligned orbits with the inner binary. So this is actually the main process which sculpts circumbinary disk, and once the disk dissipates, planetary systems. Okay. So before I begin, what I'm going to do is I'm going to actually draw an analogy. So it turns out circumbinary disks have physics very similar to just this plate, which I'm going to set spinning on this table, right? So I'm going to set this plate spinning. I'm going to give it angular momentum. And because this plate feels the vertical force from gravity, this is going to cause the disk to precess. And if we're going to measure the inclination between this disk and the table, we see that over short time scales, the inclination stays roughly constant as it's wobbling, it's precessing. But over long time scales, right, the disk feels friction from the table. And this friction exerts a torque that slowly aligns the disk with the plane of this table. All right, so it turns out circumbinary disks are very similar, right? So these circumbinary disks, when you perturb it, they excite bending waves. And so the disk itself is pretty darn close to flat. And when you torque it by this inner binary, because the disk is rotating, what it's going to do is it's going to precess the disk orbit normal, shown in blue here. It's going to precess around the binary's orbit normal, shown in brown. And this is over short time scales when the disk orbits a circular binary. This is always what happens. But the disk isn't totally flat. It has a little bit of dissipation. And if you assume that this dissipation is an isotropic viscosity, you can show that the inner disk has a slightly different orientation than the outer disk. You calculate the gravitational torque exerted on this disk by this binary because the different orientations of inner and outer disk. What you find is that over long time scales, just like this disk on the table, the circumbinary disk slowly aligns with the binary's orbital plane over a time scale less than about 10,000 years. Okay, So this is when the inner binary is circular. What we're going to do now is we're going to show how this picture changes when the inner binary is eccentric, right? So now the binary is not circular, it's eccentric. This brown arrow is again the binary's orbit normal. This red arrow points in the direction of the binary's pericenter. And when you give the disk a seed inclination, a small seed inclination with respect to the binary's orbital plane, just like the circular case, it just precesses around the binary's orbit normal. But when the binary is eccentric, if you started off at an inclination larger than this critical inclination, which gets lower as your binary gets more eccentric, instead of precessing around the binary's orbit normal, it instead precesses around the binary's pericenter direction, which is shown by the red arrow. And just like before, so if you start this disk around the eccentric binary in precessing around the binary orbit normal, the disk is just going to align with the binary's orbital plane. But you start the disk off in this state where it's precessing around the binary's pericenter direction. Again, you calculate the torque due to viscosity. Acting on this disk, this is the answer which you get. And you just let the system evolve. Instead of being driven into alignment with the binary's orbital plane, instead is driven into alignment with the binary's pericenter direction. So this is how these systems evolve into these polar aligned states. We can show this a little bit different way. We can do integrations with time of the inclination of the disk. This is the result that you get. So this binary here has an eccentricity of about 0.6. Here the critical inclination is about 30 degrees. Below the critical inclination, the disk goes into just coplanar alignment. But if you start the disk off with the higher inclination, instead of going into coplanar alignment, and instead is driven into this polar aligned state where the disk is driven into this 90-degree orientation with respect to the inner binary's plane. And so if you actually go ahead, you calculate this critical inclination here shown in the dashed line for binary eccentricities you see often in circumbinary disk systems, you find that this critical inclination is actually not too large, right? So it's somewhere between 40 to 20 degrees for typical binary eccentricities. And one thing we noticed is if this process is not disk turbulence, if it's these viscous torques that are setting the inclinations of these disks, you should expect not a bunch of inclinations, but you should expect two inclinations. One is coplanar alignment, but the other is this polar alignment with respect to the inner binary. And there shouldn't be just a few oddball systems. You should actually say more of these. And after we published this work, a number of observers actually followed up and found that, yes, there are more of these polar aligned disk systems. Showing right here, HD 98800 with gas kinematics. And looking at the continuum emission from the dust of this disk, we know that it has this polar aligned state with respect to the inner binary. And we're showing right here on the right, this recent detection of a circumbinary planet around two brown dwarf binaries, where the planet actually, again, has this polar orientation with respect to the binary's orbital plane. This was measured by looking at radial velocity observations of these brown dwarf binaries and finding negative pericenter precession. Okay, so we know there are a number of disks in this polar aligned state. There's also follow-up work looking at the inclinations of these circumbinary disk systems, and these inclinations do support the circumbinary disks ending up in one of two states, coplanar and polar alignment. So for all binary eccentricities, if the inclination starts off low, you expect it to go into coplanar alignment. For both circumbinary planets and disks, we do tend to see this. But there's this tentative evidence, so these dashed lines show degenerate solutions because there's only radial velocity binary. But there is tentative evidence that circumbinary disks, when the binary eccentricity is large, do tend to prefer this polar aligned state. Okay. I'm going to do a little bit of a brief aside, actually. So most of these inclinations were gathered through interferometric measurements. One thing that interferometry struggles just because spatial resolution has trouble resolving small spatial scales are really compact circumbinary disks. And a complementary way to constrain the orbits of really compact circumbinary disks is actually through time series photometry. What I'm showing here is this KH15D system. It consists of a binary with a nearly edge-on disk. The binary goes in and is eclipsed by the disk over short timescales. You see these large variations in the flux over the binary orbital period when the binary is going in and out, being eclipsed by the disk over long timescales, decades. This is the precession of the binary. With this undergrad student, Michael Poon, he's now a grad student, going to be applying to postdoc soon, be on the lookout for his application. We showed that you can actually use this light curve to constrain the properties of the system. Its inner and outer edge is about 1 to 5 AU, and the inclination between the inner and outer disks. There was follow-up work too. We teamed up with an amateur astronomer, actually found more of these systems with this Wiki-Transient Facility variable star catalog. And so this is actually a growing population of disks that we could get complementary information on using actually time series photometry. Okay. So back to the theory behind these things. We just discussed when the binary is on the inside. Now let's put the binary on the outside. Let's think about circumstellar disks with external binary companions. These systems differ in two ways for certain binary disks. One is that when the binary is on the outside, even when the binary is eccentric, you don't get this polar aligned kind of precession. You always precess around the binary's orbit normal. The other difference is that the interaction between the binary and the disk could be a lot weaker. So depending on how close your binary is, the torque can differ a lot in strength. So when the binary is close to the disk, the torques between the disk and the binary are very strong, and very rapidly what the disk is going to do is align with the binary's orbit normal. When the binary is very, very far, the torques are much weaker, and so you stay misaligned. And so when you actually observe these systems, both disks and once the disk goes away, planetary systems with binary companions, you expect close systems to have aligned disks and with the binary companions as well as planets. Far separation systems, you expect them to be misaligned. And generally this is what we observe. What I'm still working with collaborators to understand is the critical distance over which this separation takes place. So this is work done by Christensen in collaboration with Andrew Vandenberg, looking at test systems with visual binaries whose orbits were constrained through astrometry. And we see that when the binary companion is close, the inclinations between the planets and the external binary tends to be low. When the companion is far, you get misalignments. And this critical separation is about 700 AU. And from these viscous torques, if you calculate the alignment timescale for these viscous torques, it's really hard to get a damping timescale at 700 AU to align the disk within the disk lifetime. The rate is much too weak. So I'm working to figure out if other ways might be able to increase, if these disks might be for some reason more viscous, either due to spiral density waves or parametric instabilities excited by the warp within the disk. All right, so we talked about the first stage of planet formation. Now what we're going to do is we're going to switch gears a little bit. We're going to think about when the gas disk goes away, you're just left with the planets orbiting the host star. And so in particular, what we're going to be thinking about are these systems I circled in red: hot Jupiters, Jovian masses, orbital periods 1 to 10 days. So when we first detected these systems, we didn't expect to find them because in order to form these planets, we think they form through core accretion. In order to accrete its gaseous envelope, it has to have a 10 Earth mass core. And you only have enough solids past about 100 days where the ice line is, where we have this cold Jupiter population. And what's generally agreed upon is the way these hot Jupiters arrived at their locations is they didn't actually form there. Some process caused them to migrate in, right? But the debate in the literature, people are still trying to figure out exactly how this migration has taken place. So one class of theories argues that these hot Jupiters had a very rough and tumble past. So some gravitational interaction placed the hot Jupiter on an inclined orbit and very eccentric, either with the nearby planet or an inclined stellar companion. The time-varying tidal force exerted on the planet by the host star caused dissipation on the planet, circularized its orbit, and it left it in a short period misaligned with respect to the original plane the planet formed in. Okay, so that's encoded by the host star spin. So we expect these hot Jupiters to form misaligned with the host star spin. Disk migration argues that you have a much more quiescent history. So when the planet forms, it carves a gap in the disk. Torques between the planet and the disk cause it to migrate inward. When the gas disk dissipates and goes away, because it's very quiescent, you form a short period planet aligned with the stellar spin. All right, so as a little bit of an aside, you might naturally be wondering, you just spent the past 20 minutes talking about how disks can be misaligned, and now you want me to think that everything is quiescent, everything is aligned. Yes, you're right. These disks can be misaligned, in particular if you have a binary companion. This binary can actually misalign the orbits of planets forming in these systems. What I'm showing, not only have I shown that this is possible theoretically, I've teamed up with observers to show that there are some systems where the only possible way to explain their architectures is through this mechanism. In particular, there's K2290 here. It's two planets, nearly coplanar orbits, but the planets are actually orbiting in the opposite direction as the star at the center is spinning. And what I showed is that this likely arose because of the torque exerted on the system by the distant binary companion. And I don't have time, unfortunately, to discuss the physics of why this is. It involves something called a secular resonance, but the key takeaway here is that the reason why we're not going to be worrying about this is this mechanism can only work for warm Jupiters, not hot Jupiters. So hot Jupiters exert a very strong torque on the host star, can't misalign it. And so for hot Jupiters, the focus of today's talk, disk migration only, planets, hot Jupiters which form early, always have to be aligned with the host star spin. Okay, so now what we're going to do is we're going to look at these misalignments, right? So y-axis here, this quantity lambda projected obliquity measured through the anomalous radial velocity. You measure the angle between the stellar spin axis, shown in dashed, and the orbit normal of the planet, solid line, measured on the observer's sky plane. These inclinations are on the y-axis, x-axis, effective temperature of the host star. We're going to first look at the red points, hot host stars, effective temperatures larger than about 6100 Kelvin. We see these projected obliquities have a large smatter. This supports high centricity migration being a really common way in which these hot Jupiters form. Now what I want you to pay attention to, not the red points, but the blue points, hot Jupiters around cool stars, less than 6100 Kelvin. Right, so in sharp contrast to the red points, these blue points are all predominantly aligned in coplanar. There's not really a reason why hot Jupiters, you change the effective temperature of the host star a few hundred degrees Kelvin, you get very different results for high centricity migration. Instead, what people have rallied around as a potential explanation for this is this has something to do with the different internal structures of the star above and below what's called the craft break. So stars below the craft break, they have these big, thick convective envelopes. When they feel the tidal forcing from the hot Jupiter, these convective eddies interact with the tidal forcing, and it brings the stellar spin axis into alignment with the orbit of the hot Jupiter. So to understand how these theories work, I'm going to give a brief little primer on tidal theory. Right, so if I'm the fluid host star, and I'm being perturbed by a hot Jupiter, if I have no dissipation, my tidal bulge is going to exactly follow the location of the hot Jupiter. But I don't. I have a little bit of dissipation. This causes my fluid bulge to lag a little bit behind the hot Jupiter's location. That causes me to feel a torque. This spins me up, and it also changes the orbit of the stellar spin axis relative to the orbit of hot Jupiter. So the idea, right, with constant Q is these cool stars just have more tidal lag, more friction, lower stellar quality factors, lower Q. So you just do constant Q theory, you look at these cool stars. we look at the top panel, these obliquities for constant Q, different colors are just different planet masses. See, yes, you can align the obliquities here. We run into a problem looking at the bottom panel, these dashed lines. This is the orbital period. Soon after the obliquity is aligned, hot Jupiter is eaten by the host star. This is a problem, right? We see these hot Jupiters. So there was a proposed way around this. Lye 2012 argued that actually inertial waves might be able to damp the obliquities without engulfment. So this panel right here, bottom panel, the obliquity, we see inertial waves can align the obliquities of hot Jupiters. Top panel shows the semi-major axis. The orbit stays really far away over most of the planet's lifetime. Unfortunately, though, follow-up work has found that this theory doesn't quite work well enough. This diagram here, the dots show the results from population calculation. The black dots, the red dots here are the observed projected obliquities of these cool stars. There are too many misaligned spins. This mechanism is quite dissipative enough. And also, there's this clustering around 180 degrees. Inertial waves have a lot of trouble realigning retrograde stellar spins. And so what this led me to is maybe this isn't due to these other theories. Maybe there's something else going on. I was drawn to this theory known as resonance locking, which argues that these stars, they have these natural oscillations that can be excited by the hot Jupiter. And these oscillations can exert a back reaction torque on the orbit. And this back reaction can accelerate the tidal evolution of these systems. How this theory works right here, y-axis, so x-axis is distance to the host star and for the hot Jupiter, y-axis is dissipation rate. Orbital energy is negative, inversely proportional to distance. So positive dissipation rate means that the hot Jupiter is going to move inward, right, this way, right? Okay, so we're going to do, so the hot Jupiter, if it's over here, it's going to migrate slowly, and then it's going to go really rapidly over this hump and then slowly again. So what we're going to do is we're going to start the hot Jupiter really close to the exact resonance. You get this peak here because the hot Jupiter is forcing the host star at exactly the oscillation frequency of one of these oscillation modes. We're going to start it off really close to this exact resonance where you get this peak, and we're going to think about what the system does. Okay, so put the hot Jupiter close to this resonance. What's going to happen is it's going to move pretty quickly away from this resonance. Nothing else is going on. It's just going to go to this trough, and it's going to march along due to whatever constant Q theory gives you evolution at this trough. But this isn't the whole story. It's a star evolves, hydrogen goes into helium, core contracts, that increases the Bront bisolid frequencies and the frequencies of these oscillations gravity modes. And that moves this resonant location inward just a little bit, right? And there's a location, this hot Jupiter can resonantly lock onto this oscillation. That's why this theory has this name, resonance locking. And this lock accelerates the tidal evolution as these gravity mode frequencies evolve. Right? So this is how this theory works. So why you expect this to work more for cool stars? The oscillations these hot Jupiters lock onto, I like to call them rubber duck frequencies. You have a rubber duck in the bathtub, pull it down, let it go, bobs up and down. Characteristic frequency, that's N right here. Bront bisolid frequency. These G modes only propagate in the stably stratified radiative regions of the star. So both cool stars and hot stars, as they evolve along the main sequence, their cores contract. The difference is their internal structures. So for cool stars, they have these radiative cores where the G modes live. And so as the core contracts, they really feel this contraction really strongly. That increases the Bront bisolid frequency, and that increases all the frequencies of these G modes. Hot stars, on the other hand, their G modes live in the suburbs, not where all the contraction is happening. And so their G modes stay roughly constant. If you remember before, right, resonance locking argues that the main reason these that you get this dissipation in the first place is the evolution of these G modes. And so we're arguing here that this acceleration due to the radiative core evolving these G modes more is because of the radiative core, not the convective envelope. It's the radiative core that is driving this increased tidal dissipation for these cool hosts. All right, so this is why we get more dissipation. We're going to talk about now is what resonance locking is actually going to do to the orbits, right? So We're going to think about the geometry of one of these oscillations. So I'm showing right here an axis symmetric m=0 oscillation. So stellar spin is j hat star. If we look down the stellar spin axis, it's just going to be a circle moving in and out, has azimuthal number of 0. What we're going to do is we're going to think about how this oscillation interacts with the orbit of hot Jupiter, how it gets excited in the first place. We're showing these colors. The radial force from the tidal forcing of the hot Jupiter. Red is being pulled, is outward, red is inward, blue is outward. So we see at this point, this oscillation is being pulled out really strongly. At another point of the equator, it's all being pushed in. And so when the hot Jupiter is highly inclined to the stellar spin, you can excite this axis symmetric oscillation, but due to the hot Jupiter's tidal force. So once this thing is excited, it's going to interact with the orbit. We want to figure out what it does to the stellar spin. So we want to calculate the torque, right? So in this system, we're going to have the stellar spin axis in the z direction. We're going to tilt the orbit normal of hot Jupiter in the xz plane. What we want to do is want to figure out how the stellar spin, j hat star, is going to evolve relative to the orbit, j hat orbit. And so what we want to do is we want to calculate the torque in the x direction. So to do this, what we want to do is want to figure out how the true location of the hot Jupiter, shown in purple, is ahead of where the tidal forcing from the hot Jupiter would exactly balance the oscillation bulge, shown in light purple. And we're going to calculate the torque exerted on the star. So to do this, we want to peer down the x-axis to calculate the torque in the x direction. So that's what we're doing right now, right? So we're peering down the x-axis. So red is the tidal bulge, blue is the force. From our torques, or R cross F, right? So we have the bulge, force, get a torque. It's pointing out of the projector screen. So if I'm the stellar spin axis and I'm feeling this torque out, what I'm going to do is I'm going to move out of the projector screen into alignment with the hot Jupiter's orbit. All right, and this is at one snapshot at a time. Let the hot Jupiter go along its orbit. We see that the torque is always going to be positive. And so the stellar spin is going to always be driven into alignment with the orbit normal. Okay, so you might ask though, so this is one oscillation. There are a lot of different oscillations that can be excited by the hot Jupiter's orbits when it's inclined. In particular, depending on the obliquity, you can get a lot of different types of oscillations that are excited at a number of different azimuthal numbers m. And so when the obliquity is low, you primarily excite this m=2 oscillation. As the obliquity gets larger and larger, you excite, it's easier to excite lower and lower azimuthal numbers. What I want you to take away here is that for all of these oscillations, the obliquity, we did this follow-up work, we found that all of these different oscillations, they all damp the obliquity. They always drive the stellar spin into alignment with the hot Jupiter. And so we know no matter what oscillation the hot Jupiter excites, cool stars are always going to have their obliquities damped by this mechanism. Okay. So I've just discussed how resonance locking can damp the obliquities, but what I haven't really done is explain why this mechanism is special, right? So left-hand panel here, this just shows what I talked about in the beginning of the talk, equilibrium tides, where the bulge is closely following the location on the hot Jupiter. Right-hand panel shows this axisymmetric oscillation excited by resonance locking. To explain why this works, what I'm going to do is I'm going to draw an analogy where between an owner walking its dog in the system, and in this analogy, the bulge is the dog, the owner is the hot Jupiter, and the leash is the tidal force between the two. And so what equilibrium tides argues is that the bulge is always closely following the location of the hot Jupiter. It's a very well-behaved dog. And because you get this limited interaction between the hot Jupiter and the star, you really limit the type of dynamical behavior you get from this system. Resonance locking, on the other hand, it gives the bulge or the dog a lot of freedom. It doesn't always have to follow the location of the hot Jupiter. You can excite all sorts of different oscillations which interact in different ways with the hot Jupiter. If you ever walked a dog with a mind of its own, you know that your system can encounter unexpected dynamical behavior. And so by freeing the assumption that the bulge always has to follow the hot Jupiter, you get a lot of interesting behavior in your system. Okay, so we have our two ingredients. We know that cool stars dissipate more due to resonance locking. And when they dissipate, they also damp the obliquities. What we're going to do now is we're going to show some calculations to show how effective this is at explaining this correlation between projected obliquity of hot Jupiter systems and the effective temperature of the host star. So the left-hand panel shows the obliquity with time for systems hot Jupiters undergoing resonance locking. Blue are cool hosts, red are hot, right? So we see that these cool hosts, over less than half of the main sequence lifetime, damp their obliquities all the way to 0. Hot stars, on the other hand, they stay highly misaligned. And so we see that resonance locking, like expected, is good at damping obliquities. Right-hand panel shows the semi-major axis. Unlike equilibrium tides, way after these hot Jupiters have their obliquities aligned, they stay pretty far from their host star. And so the hot Jupiters are not engulfed soon after they're aligned. So this is promising. We can do this, show this result a little bit different way too. We can do a population synthesis calculation. We not only include one oscillation, we can include all of the oscillations. We start hot stars and cool stars off at the same obliquity distribution. We let the system undergo resonance locking. We include all the different ingredients. You can vary the location of the hot Jupiter's mass. We can let the star spin down. We include all the ingredients here. This is the result we get. So filled squares here. These are the observed obliquities. Open squares, this is the theory. Just all first principles MESA calculations, no free parameters anywhere. Hot stars, red points, just like we observed, stay misaligned. Blue points, cool host stars, all have much lower obliquities. There are a few stragglers that we're a little bit worried about that we don't observe. But my collaborators and I, we are encouraged by this result. Okay. However, there's something important which I've glossed over, and that's actually how this dissipation takes place. So I'm showing here in this curve is the energy dissipation rate near one of these exact resonances. Solid line shows what you get with just linear dissipation of these gravity modes from radiative diffusion. You get this sharp peak near the resonance, which is what you need for resonance locking to work. These crosses here show what happens if you include nonlinear mode-mode interactions. And so this resonant oscillation can couple to higher order G modes, siphon its energy off. And instead of getting this sharp peak, these crosses argue, these nonlinear interactions proposed by Essig and Weinberg argue that instead you actually get this flat line. And if this is how this interaction takes place, this is also the metaphorical flat line of our theory's cardiogram because it's dead, right? These closed circles, though, show what happens if you take a close look at these higher order oscillations, and you find that actually they become so large that it causes this core of the star to be convectively unstable. So these oscillations actually become traveling waves, not standing waves. And if you take this into account, instead of getting this flat line, these nonlinear interactions get you this blunted Lorentzian, and you recover this resonance. So this is work I'm working on right now, trying to do hydrodynamical simulations to verify that this is actually what occurs. But this is the major outstanding problem of this theory, which I'm still working on. Okay, so I'll conclude the talk. So we argued that fluid interactions can play a large role in sculpting the diversity of exoplanets. So when the planets are still forming the disk, viscous torques between the disk and the binary companion play a large role in setting their inclinations. What I'm working on right now is figuring out the details of how these inclinations are sculpted for protostellar disks with external binary companions. And once the disk dissipates, interactions between hot Jupiters and their host star can explain these correlations we see between the projected obliquity and the host star's effective temperature. So thanks so much for coming to my talk, and I'll take any questions if you have them.
That was great.
That was really interesting. I'm curious in the first part of the talk, maybe you said something and I missed it, or maybe I'm misunderstanding something. The critical inclination that you start with, depending that sets the polar or aligned, seem to only depend on the eccentricity of the companion.
Mm-hmm.
Are you skipping over? Is there a mass ratio?
Yeah, there is
In
actually.
there that's less important, or?
Yeah, that's an excellent question. Yeah, so mass ratio does actually affect things a little bit. So in particular, if you switch it the other way, so it's like the limit where the disk is massless and you have just the inner binary, you switch the mass ratio, the external companion is the most massive and the inner one is a test particle, you get cosi, right? And so that instance, the critical inclination is always 40 degrees. And so yes, the mass ratio is important. But for typical circumbinary disk systems, the ratio of the angular momenta is such that if you include it, it only causes this, it's less than 10 degrees. And so
I guess I was wondering if you get could you get, is there some critical inclination that matters for systems where you have a companion that you might not see, like a 10 to 1 or something like that?
Yeah.
I'm thinking of observing these things and what
Yeah.
might be missing in transition disks if there's brown dwarf companions.
Yeah, no, that's an excellent question. Yeah, so for instance, like HD 89880, it's got another binary companion. Also, the brown dwarf system, it's also got a stellar companion. So these things do modify things, but for circumbinary disks, and also circumbinary planets, they tend to be pretty close to inner binary. And you can calculate the ratio of these torques, and it just generally, the inner binary always wins because they're always so close. But yeah, those do modify the dynamics, and there have been papers on
Yeah, again, on the circumbinary disk stuff, you keep talking about viscosity.
Mm-hmm.
This is a faraway disk, right?
Yes.
It's not magnetorotational viscosity, is it? What kind of viscosity is it you're talking about?
It could be magnetorotational viscosity, but of course the disk has to be ionized. They're dead zones.
Yeah.
Honestly, I'm sure you know with like high energy disks, we're still trying to figure it out, right? So you can probe it by accretion rates. So accretion rates, you can get an estimate of the viscosity. If you estimate alpha due to typical accretion rates for protostellar systems, you get variations by like 5 orders of magnitude. And so it's not actually clear what the viscosity of these systems is. That's still an outstanding problem in this field, just like it is for yours. But yeah, even if there's just a small amount of viscosity, these circumbinary disks will be driven into this polar aligned state because this interaction is so strong.
So strong.
Yeah.
But still, I was just wondering, the time scale must tell you something about the magnitude of viscosity. Is there any information from the observations?
Yeah, so that's a good question, right? So it reminds me that I heard a quip, there's only 3 numbers in physics, right? 0, 1, and infinity. So for these circumbinary disks, we tend to find they're all, so you can actually place limits. So this alignment timescale for typical parameters is about like 10,000 years. So that's alpha of 10 to the minus 2. You increase that to 10 to the minus 4 or 5. This alignment timescale is proportional to alpha. And so it's got to be less than 1 million years, and that places like alpha less than like 10 to the minus 4 or 10 to the minus 5. But there's a wide range of freedom there just because we see these systems to all be aligned.
You meant greater than 10 to the minus 5?
Smaller than 10 to the, yes, greater than, yeah, you're
Greater
right.
than,
Yeah, absolutely, yeah.
Which is probably kind of similar to what people talk about anyway, right? From FU Orionis systems or whatever. I think alpha toggles between 10⁻²⁴ and -4 is the number I remember
Yeah.
from long ago.
Yeah.
So you're saying that it's kind of roughly consistent. But
Yeah,
I would love to know what the viscosity is. Because
Yeah.
if it is cold enough and it's not magnetic fields,
yeah.
what is it? Is it particles? Is it icebergs hitting each other, or what is it? Yeah.
Yeah, no, I'd love to know too. Yeah. Yeah, so people are still trying to figure it out. There's all sorts of different constraints. Particularly if we go back to those dust rings, you get one constraint on viscosity there, because viscosity causes those dust particles to diffuse. Like you get a constraint there of like 10⁻³ ish, 10⁻⁴. And so there's all sorts of different ways you can hack at it, and you get all sorts of different. There's also in protoplanetary just the idea that accretion isn't even due to viscosity. So maybe the viscosity is actually zero, but I mean, we see these things to all be aligned. So that does point, at least to me, for something happening for the circumbinary disk systems, presence of some viscosity to go ahead and align the disk with the binary circle. Yeah, yeah, yeah.
Thank you. I was curious about what happens with the if you have when you go to the lowest mass end
Mhm.
for like M dwarfs and your radiative core starts to go away. What happens to your G modes then?
Yeah, it's an excellent question. The G modes don't exist. And so for M dwarfs, this mechanism doesn't work, right? So for M dwarf stars, if you see that all the hot Jupiters around M dwarfs are all predominantly aligned, that can't be due to this mechanism. So that maybe, so M dwarfs, hot Jupiters have a different occurrence rate. Maybe they form differently. They don't undergo this high eccentricity migration the same way. This could also be one of the ways in which this theory is disproven as well. So if you see this alignment persist, there are a number of recent detections of aligned stars for hot Jupiters around M dwarfs. If this does persist, that this theory can't explain that. So yeah.
Yeah, thank you so much for your talk. I think on the disk alignment side, so you mentioned that there's like this critical like inclination you have to hit. Like, do we have any idea of like what the like sort of seed inclinations like distribution is like among disks, or like what could cause like that initial like inclination to then
Yeah, good question. Yeah, so like the distribution is just going to reflect the binary eccentricity distribution, and so that's. You find it's like somewhere between, you start like eccentricities of like 0.3 to 0.8, so between like 60 degrees to 20 degrees. What the seed inclination is likely due to is turbulence. So turbulence like can set the stage, but the thing that sculpts the inclinations of circumbinary disks that we actually observe, that is likely due to these viscous torques from disk warping, because we tend to observe the disk in one or two states, this classical alignment and this polar alignment. Yeah.
Thank you again.
After you came here, yeah. Good to have you here, yes.
Good to be back.
Yeah.
I just went to the office for the first time yesterday.
Oh. No, next to me.
That's
Good
really
job.
time.
Yeah, good to see you. Yeah, it's good to see you more. Yeah. Yeah, it's good to see you. Yeah.
How you doing?
Great talk. Sorry for wandering in a few minutes late.
Yeah. So, okay. Can I keep it there?
Oh, we both want to set your.
Should be okay.
Okay.
Let's just present it.
Pretty good.
It's like fairly high. Maybe like really introduce it. Yeah, and like it's like.
Oh, see you. Yeah, see you personally.
Yeah, looking forward to this talk.
Yeah, thanks. Yeah, look forward to our podcast.
Yeah, me too.
Yeah.
But. Like a little bit more interesting, like, yeah. I was.
It's not.
Yes. So did you get the email?
Yeah.
Capito. Capito.
Parla un po' italiano, questo è morto.
Yeah.
You and I've been friends for 22 years. He was like for more than a decade, getting over a decade, like the president of the Italian Astronomers Association. So that's it. Tons of stuff. I love that. I love that. Yeah, exactly.
Yeah,
That's what I always feel. Like,
Sure.
it's like if you can make a telescope in your yard work.
What's up?
Like the first night.
Oh, JJ. Yeah. All the 2 letters. It's a BC, like. Excellent. Okay, good. Yeah, what was your name?
Shohan.
Good to meet Shohan.
Good to meet you.
Yeah.
There's a telescope operator who points it. It tries. Well, it like.
Oh, I can admit people in. Oh my god.
Like,
Oh, is that?
camera work.
I just so like I can like admit people in. I admitted PC. So. Oh my god.
Yeah, well, because in order to, like, a thing to present, like.
Yeah. So like we made goals.
Exactly. So I like. I grew up doing things with all those things. So I'm like doing it myself. It's like, yeah, you realize how better you have to know what you're doing. Yeah.
So where are you folks from?
I'm from.
Oh, okay, very nice. Yeah.
Sorry, I didn't catch that.
No, I'm from Harriet University in Israel. Okay. So I'm physics in MK High, MIT Complex School.
Where was that? Like in Israel? Is it like near Tel Aviv or Haifa or? Is this not that right?
Kilometers from here, from Tel Aviv, east of Tel Aviv.
Okay. I'm from UVA, University of Virginia.
Oh, cool. Yeah, do you know, Default Jackson?
Yeah.
We thought that, yeah.
Oh, that's he. Ah.
But, yeah, he's a great guy. I love him.
Yeah.
And, yeah.
Why don't you sit right here? Okay, and if we wanna test your thing,
Oh, yeah.
we can do that?
Yes.
Yeah, okay. Sorry, I'm just getting them.
Yeah.
You're gonna be talking about supernova remnants?
Yeah. Well, I'm curious.
So.
Sorry, what?
Okay. It's great to see everyone in this small room. It makes us feel like a community. But it's just because there is a conference in Philips. Otherwise, we would like people to have their space. After all, we are all focused on space. Space is limited in this room, but we will get the science. A couple of things. One, next week I'll be attending a conference in Germany, so Fabio will take care in my absence of lunch. And another is that NASA announced yesterday, as many of you heard, that after studying a rock, I mean, there was a paper in Nature that passed through peer review. They announced that it's quite likely that what they see on the rock is evidence for microbes that generated those patterns, that these dots that they see there. And however, it could also be some geological process. They cannot be sure unless we bring the material back. There was a sample return mission that was planned, if many of you remember, from, I think it was around October, November last year, 2024, when it was announced that it will be a priority for NASA, but now with the budget cuts, that was taken off the table, and the new NASA, the interim administrator of NASA said yesterday that they would try to find the money, doing it quicker and more efficiently, to bring a sample back to Earth so that we can analyze and figure out if there were microbes on Mars. And I mean, it will not be surprising given that there was liquid water, and you can see the way that the rock looks like. It looks like a dry lake. What you see after water was there, like the patterns, and it's quite likely that Mars even had life before they appeared on Earth, and some of this life was delivered to Earth, so we are all Martians, and microbes were the first astronauts. They were delivered inside a rock. They were the first tiny astronauts that were much more accomplished than Elon Musk. They made it to Earth from Mars, billions of years ago. But hopefully there will be a sample return mission, so we will know the answer, and that will be, of course, astrobiology, knowing that there is life elsewhere, although it's just a rock close to Earth, so it's not surprising in the solar system to find life on Mars in the past. Anyway, that's exciting, and we all look forward to sample return to Earth. So we just heard an ITC Colloquium. Do you call yourself JJ or John?
Oh, I prefer JJ.
Yeah. JJ Zanazzi gave an excellent presentation today, and we will hear from him again about the diary of a teenage super Jupiter. I'll mention also other talks. Nowadays, I don't know if teenagers write diaries, right? At the very least, AI does it for them. And then we'll hear from BC Bernard Ogunwale. Ogunwale. Yeah. Nice, because usually the last E is not pronounced. Yeah. He is from Ariel University, and he will tell us about catalog of variable sources in tests full frame images. And after that, we'll hear from Chan Huang from Washington University in St. Louis, who will tell us about neutron stars in full color, unifying multi-messenger echoes to reveal nature's densest matter. And finally, we'll hear from Soham Mandal from the University of Virginia. I hope Soham is here somewhere. Yeah. Oh, he's there. Okay. Yeah. And he will tell us about stellar forensics, tracing the origin of thermonuclear supernova remnants and interaction supernova. Great.
Thanks so much for the invitation too, by the way. So I'm currently a postdoc at Penn State. I'm going to be starting fall 2026 as faculty there. So to set the stage, right? So I'm a planet formation theorist. In our own solar system, a lot of things vibrate. So every time on the Earth, there's an earthquake, pressure and shear waves propagate across the lithosphere. You look at the sun, it supports these few-minute oscillations due to pressure modes. And Saturn supports these surface gravity waves, which cause the gravitational field around the planet to oscillate. And the effect of this is to cause the rings of Saturn to have spiral density waves driven away from the planet, shown here in the Cassini data. In addition to working as a seismograph, these oscillations in the rings also extract energy from the planets, damping their mode amplitudes. And so something actually has to have happened pretty recent to excite these oscillations. What's motivating for the stuff we're going to be talking about today is this paper of Will and Lithwick, who argue that the reason we observe these oscillations is in the past 40,000 years, Saturn was slammed into a 25-kilometer planetesimal that excited these observations, which we observe. And one thing that's interesting also for today's talk is if these rings actually didn't exist, they pointed out these oscillations in their words would live virtually forever. There's not enough dissipation on the planet to damp their amplitudes. So it's not just planets in the solar system. So there's other evidence that things in the solar system have suffered giant impacts. So Uranus has a large obliquity, likely due to an impact. Jupiter's fuzzy core might be due to an impact with a Neptune mass body. There's also these measurements from Thorngren et al. Using bulk density estimates of exoplanets, they infer the bulk metallicities of these planets to be very, very high. In particular, what I want you to draw your attention to is this line right here denoting 100 Earth masses worth of solid material. And it's very hard to get this amount of solids in Jovian mass planets because in order to form these planets, you have to have a 10 Earth mass core to undergo core accretion. It's really hard to get 100. And so what Ginsburg and Chang argue is that you're actually force feeding these planets solids. So they don't just have the core from core accretion. As they evolve and grow, different planets merge and grow their core to these 100 Earth mass values. And one particular gas giant that's going to be the particular interest for today's talk is Beta Pig b. So atmospheric retrievals imply this planet might be particularly metal rich, somewhere between 100 to 300 Earth masses. There's also other signatures that it might have had suffered impacts in its past. It's got a pretty big eccentricity, maybe from something slamming into it in its debris disk. And what's particularly relevant is that this planet is very young, so it's very bright. And so any impact it would have suffered will not have a whole lot of time to damp any oscillations which it experienced. What we're going to talk about today for this well-studied exoplanet is if we can actually detect these oscillations using NIRCam from JDBST. So to do this, what we're going to do is we're going to take a MESA model of a 13 Jupiter mass object, and we're just going to drop Neptune onto it. And we're going to calculate the types of oscillations this excites with the gyre code for this very young model of a 13 Jupiter mass object. And we're going to figure out if these are going to cause fluctuations which are detectable, and we're also going to calculate their damping timescales to figure out how long they're going to persist. All right. So I'm showing right here oscillations we're going to be considering. So red and blue denotes temperature excesses or deficits due to the oscillation modes that get excited by this impact. These two letters categorize the modes. So N tells you information about its radial wavelength. You look at the low N oscillations on top, you look at their interiors, they have larger radial wavelengths than the modes at the bottom. The angular degree L, this tells you the angular wavelength. L equals 0 is axis symmetric. Okay, L equal 2, they have shorter angular wavelengths. This panel on the right hand, this right-hand panel here shows the periods of these different oscillation modes we're going to be considering in this calculation. The size of the symbol tells you the radial node number N. Bigger symbols denote larger radial wavelengths. The x-axis shows the angular degree L. And what I want to draw your attention to is that these points up here, these largest wavelength radial modes, their periods are around somewhere between 30 minutes to an hour because JDBST's NIRCam instrument has a cadence of around 3 minutes. You might actually be able to resolve these. Okay, so you might actually see these oscillations, these large wavelength oscillations in NIRCam. What we're going to do now is we're going to think about the amplitudes they get excited to and how long they're going to damp. And so after you drop Neptune onto it, the momentum of the impact is imparted into the oscillation. If you calculate the displacement amplitudes of these oscillations, it just turns out to be the mass of the impact over the mass of the planet. This has a value of around 1%, maybe a little bit higher if you do the calculation in a little bit more detail. So once you excite these things, these large wavelength oscillations, it turns out the way they diffuse their energy is through diffusion. And because they damp through diffusion, the timescale these modes damp is just the timescale that energy just generally leaks from the planet because their wavelengths are so large. That's the Kelvin-Helmholtz timescale, the binding energy of the planet over its luminosity. And because the planet heats due to gravitational contraction, this timescale is the planet's age. So you naturally get that these oscillations, which are excited to percent levels, persist over the age of the planet. Okay, so these things, so this is how they get excited and damped. Let's show this in a little bit more detailed way. Right, so the y-axis here, this is showing the observed luminosity variations from these oscillations that get excited. Different panels show different snapshots in time. And so the first one is right after the impact. A lot of oscillations get excited, but if you wait long enough, all the other oscillations die out and you're just left with one oscillation which causes flux variations of around 1%. It turns out this oscillation is the simplest one that you could imagine. It's just the whole planet's heating and cooling axisymmetrically. And so this oscillation persists for like a very long time over a time scale of, okay, all right, okay. Yeah, no, it's all good. Okay, all right, so it persists for a very long time over a time scale comparable to the planet's age. So this is potentially observable. So what we did is figure out how likely we are to see this with NIRCam. We teamed up with Yifan Zhou, who did this calculation I'm showing here. The left-hand panel, this is a simulated observation using NIRCam. We're injecting noise due to spectral photon and stellar variability into the light curve, as well as the signal from this 40-minute oscillation. Right-hand panel shows the Lumsgargle periodogram after applied to the left hand. We say we're able to actually recover the period of this oscillation with a greater than 5 sigma false alarm probability. So you actually might be able to detect these with the NIRCam instrument. So stepping back a little bit, these oscillations give you a picture of the history of these young planets. They work like a diary, right, for these teenage super Jupiters. And if we were to get a hold of Beta Pig's diary, we're going to open it up and flip 9 million years into the past. We might find this diary entry might say is something like, today was the worst. Just minding my own business on an orbit. And out of nowhere, this Neptune, which I never really liked, just slammed into me. And I'm still ringing due to this event, right? And as a planet formation theorist, I'm nosy. I want to know about this diary entry. And so what I'm doing is I'm looking at NIRCam data for JWST to figure out if I can detect this signal. So thanks so much for the invitation. I'll take any questions if you have them.
So JJ, during the impact, is there a flare that we should be able to detect if we look throughout the galaxy?
Yeah. So there should be. So in addition to imparting its momentum, it should also impart. Like there's actually an impact observed on a Jupiter as well, and yeah, you do detect a flare. Yeah, but its amplitude is going to have you can whip it out. It's going to have a similar order of magnitude, but it's very, very short now.
Yeah. So then the chance of seeing it is negative.
Yeah.
Go ahead.
I wanted to ask you more about the kinetic energy and the thermal energy that you add. So when you collide, you add a lot of heat.
Yes.
And that comes out as an increased luminosity for some period of time. So isn't the dissipation at first much more rapid and then only later becomes this slow?
Yeah. So that's an excellent question. So this, in addition to imparting its momentum, this heat actually does work on the oscillation. Yeah, it's actually funny. You work it out. So it turns out the work that this work this impact can do, it excites the oscillations to a comparable magnitude as the momentum, just because like the kinetic energy over the planet binding energy turns out to be a similar order of magnitude as the momentum you impart if you drop it at the escape velocity. So it is gonna, like, just like the momentum, it's gonna cause a large spectrum of oscillations to get excited. But again, you just wait long enough and you just expect to see one single oscillation.
Totally, but isn't the post-excitation dissipation?
Yeah.
Isn't that dissipation rate set by the much higher luminosity post-impact from all the thermal energy that you added?
So right now what we're doing is we're assuming, so you're saying that the additional thermal energy actually increases the luminosity.
Mhm.
Oh, okay. Yeah, so if you calculate the maximum thermal energy, it's like basically it's going to be the kinetic energy of the planet over the binding energy of the planet. That actually has the same order of magnitude. Like it's basically still around 1%. So it's only going to
it's only a subtle.
Yeah.
Okay.
And what happens to the object? Does the planet sink to the center or get dispersed?
Yeah. So it's it sinks to the center. There's this idea that I mentioned before. That once it sinks to the center, you actually change the solid content, and that might make the core stably strong. The idea that one of the ways in which Jupiter's core could be fuzzy, it's due to the rocky material from this impact sinking to the core, changing the structure of the planet itself. Yeah. There's all.
I got a question too.
Yeah, go ahead.
Yeah.
Yeah. Okay, so the first thing I want to say is I have 4 teenage daughters. Should you ever come across a diary in the household, you do not. Let's keep that in mind.
Okay,
Right.
that's good to know.
My question is, so you just modeled the radially symmetric mode. Okay. Did you also think about, if you have slightly higher order modes, then of course that's coupled to rotation, right? So those modes are going on, but now you have this temporal scan because it's rotating. And it's oblique. Okay, so that has a perturbation. And it's oblate. And I just was wondering to what extent you thought of how big the next mode would be and whether you could get access, because then you would get access to all sorts of things.
Yes, I completely agree.
And what is that like 1/10 the amplitude of this mode, or do you think that those modes will just be absent?
Yeah, no, that's an excellent question. So like you might be able to, so asteroid seismology through these.
Like, that's what I'm,
yeah.
So it's the next.
Yeah. So that's going to change the properties of the mode. So it's so the rotation is basically going to modify the frequency as like the rotation period of the planet over. The frequencies of these modes are ordered the dynamical frequency. So yes, this could probe the rotation of the planet, but it's going to depend on how quickly rotating the planet is. It's like 10%. Yeah.
Is this one of those where we do know the rotation from spectroscopy?
So you only know the projected rotation rate. Yeah. So actually, Yifan just got this is unpublished. He got the true rotation from the variability of the source, and it looks like it's actually aligned the rotation rate with the orbit of the planet. But this is upcoming, and this is hard work. There's a lot of other stuff he's working on, but yeah. Right now, the published, you only know the projected rotation rate.
Thank you.
But the highest probability is for it to actually give it some spin, right? That it will not collide head on.
Yeah.
So then how much rotation do you get from that?
Yeah, that's going to be, you basically just, So you calculate the, how this torque, yeah. So, it's basically going to depend on exactly where.
Yeah, but the cross section proportional to area. So most of the chances is at the,
Yes.
So then it will be significant rotation because it comes at the escape speed.
Yeah. Let's see here.
It's likely to be close to.
Yeah.
So breakup. So the
Okay,
question
so
is the data
surviving,
consistent?
is that
Yeah, exactly. Is the data consistent with such a high rotation?
Yeah. So it's so from when I know this rotation rate, I think it's like a few hours, and so it's not exactly so the dynamical frequency.
Oh, no, that's very slow.
Yeah, the dynamical frequency is like around an hour. But this is also going to depend on if you have a circumplanetary disk sometime after, right? That's going to magnetic. Yeah, there's plenty of ways for me as a theorist to weasel my way out of this rotation, right?
We will not give you an easy time because you are surrounded by theories here.
Yeah, that's an
There are
excellent
only
point.
observers.
Yeah.
you could make it.
Yeah, but no, that's an excellent point. Yeah, that does send an addition, that does place an additional constraint that makes this a little bit harder, yeah.
If there are no more questions, let's thank JJ again.
Yeah.
It's yeah, it's so just yeah. This slide.
Excuse me. There's a chair here. Yeah.
Right. Thank you for having me. Grateful for the invitation. My name is Ogunwale. Yeah, some people pronounce it Ogunwale. Yeah, so it's Ogunwale, and I'm a PhD candidate from Area University in Israel, working under the supervision of Professor Greta and Dr. Lev Talon. I want to thank our 40 agencies, Israel Ministry of Science Foundation, Israel Science Foundation, and then Ministry of Innovation, Science and Technology. So today I want to talk about a new catalog which we are creating from test FFI named Tequila, catalog of variable sources in test full frame images. And this, this is the research group which I belong to, led by Dr. Lev Talon, and we do all sorts of science, stellar activity and exoplanet, but I'll be focusing on my own field, which is test FFI photometry. And this talk is based on this paper, which is presently at advanced stage. We are now reviewing the referee report, and very soon it will be available. As I've said, I'm working with Dr. Lev, Professor Greta, and then Dr. Volker from Weizmann Institute of Science in Israel, and also myself from Hamburg University of Science and Applied Science and Technology in Germany. Okay, so here is test field of view. It's observed the sky every 27 days in a part of the sky in 27 days, and then carry out almost scan the sky in almost the entire night sky. A part of it in every 27 days. The mission is to detect exoplanets around bright sources in solar neighborhood, but because of this observation technique, it makes it a very powerful and a useful mission to study stellar variability and transient events. And then this is test FFI, so it collects target pixel files and also the full frame images of the sky, of those parts of the sky. And as we can see here, it observes this huge part of the sky, and it provides opportunity to study anything that transient or variable sources in the night sky. And many projects have created light cores from this FFI. But most at times in all of these projects, they take input from, say, test input catalog, and they have predetermined target in mind, and then they do photometry for it. And most of the cases, you say that they are actually interested in transiting exoplanet, which what the system is actually built for. But outside this, when we remove everything that is constant in the field of view, what do we left with, and how can we have light curves for all these sources that probably have abandoned over the years in tests? And this forms our motivation for this project, to conduct a blind search of variable source, so no predetermined source in mind before carrying out the photometry, and then create the light curves for this for all of these sources. How do we do this? First, we take the raw FFIs, download the calibrated FFIs from MAST, and then pre-process them by extracting essential information from the FFIs, remove all FFI with quality flags, and then trim it, align. So this form our pre-processing, and then we create reference image. In this stage, there are many methods that people create their own reference image. Some choose based on certain criteria to create a reference image, but we stack all the FFIs. First, we media stack the 50 images, and then we created an intermediate product, and after that, we stack it again to create the final reference image. And then, if we are aware with tests, there is problem of background, effectively removing determining the background and subtracting it. So instead of subtracting, we are determining the background from the preprocessed FFI, we subtract these reference images, create the residual image, and on the residual image, we create the background so that the constant sources in this in the FFI do not bias our background determination. And from that, we subtract the model, the background model from the processed FFI, and we go over the process again. Go to the residual. So after just one iteration, subsequent one do not improve the photometry in general. So we just do this once. And on the residual image, here is the portion of a residual image of a star that varies over time, and we say from time to time on the residual they vary. Outside that is also spatial variation for objects that vary on the field of view that are not constant. They are also left on the residual image, and this is also a great product for us as well. So we can get light curves for temporal variation and then a spatial variation. So then we detect the sources that are above 3 sigma. We take that as a candidate for the for variable source on the field of view, and then we compile it to light curves. So the result for the first 2 years of test, we got over 6 million light curves. And then here are the samples. This is just a comparison with QLP on top, and then our product at the bottom panel. So for non-eclipsing binaries, because we remove any object, any FFI that has quality flags, some points are missing in the data. So what do we find outside those ones? Dwarf novae. This is a dwarf novae we find in sector 2 by just eyeballing, and then we search for where is this coming from, and there is no report for it. Only that there is a Gaia ID of that source that says that it's a white dwarf there. Okay, what could it be? And then another source has seen 15 Hedel in sector 16. These are dwarf novae, and all reported variables that we found. So for this in sector 2, and for this in sector 16, what are they? So we have lots of objects like this that do not have any designation. So outside the spatial variation, outside the temporal variation, we have this spatial variation as well. This is a coordinate plot of the all extracted sources in an FFI, and we can see these traces, these stripes on the image. These are the path of asteroid that is crossing the 10th field of view during the observation. And in the light curves, they come in this as this bump in this light curves. So data access. Presently, we've submitted this to our catalog to MAST for hosting, and we are at the advanced stage with them. Hopefully, by the time the paper is finally accepted, it will be made, the catalog will be made available. But outside that, we are also developing a local repository, which we call Sky Searcher. This will enable researchers to query the light curves and then get the characteristics of these light curves even first before going forward with further analysis of it. Okay, so thank you very much. Here is the summary page.
Thank you, BC. Was there any unusual source that nobody expected, anything that we've never seen before?
Well, we have, as I said, we have a bunch of data that even by mere looking, sometimes I just look at them and okay, what is this actually? I can't give any explanation to them. So we have a lot of all of this in the catalog.
These are periodic or flare?
Some are periodic, some are aperiodic.
Some are just one-time
events. Yeah.
So follow-up observations we need.
Yeah. So and also other things that we are doing presently is to map any object that belongs to a solar system object, so that we have a summary page for a summary file for each CCD. So to tell, okay, maybe this belongs to the event that you are saying, this belongs to a solar system object if it's flagged yes, and then you can determine whether or not or what you are looking for.
Okay. Go ahead, Eric.
Have any plans to follow up on some of these sources to figure out what they are and identify them?
Yeah, sorry, I forgot to mention that even presently we ourselves, from one of the sources that we found, a dwarf novae, we found it quite interesting, and presently we are also working on it. But tests for the dwarf, for one of the dwarf novae that we found, we just know that there's a white dwarf there. There is no other information that we know about this source. So it will be good for us to say take the spectroscopy of this area of the sky and determine what type of object that is there. And but for tests, it will have observed. I mean, it will have been a past event, and if the event is no longer there, there will be no need for follow-up.
Okay. Any other questions? No. Thank you so much.
Oh, yeah.
Okay. Hello. Hello everyone. My name is Chun. I come from Washington University. Work on neutron star thing. So we already listened a little bit about the normal objects. We will go to some monster thing. That is the neutron star. Yeah, that is the monster. That is the monster. So when there is a low mass star, when it explodes, it will become a white dwarf. But it will. However, if a very heavy neutron star, very heavy star explode, it will become a neutron star, or even heavier will become a black hole. How to think about that? Well, if you think about Boston, yeah, that's I changed this. Just yeah. If you think about Boston, neutron star is comparable size with Boston. It's squeezed the one solar mass matter inside of size comparable to Boston. And how to imagine that if that is not clear? Well, if you take 1 teaspoon of neutron star matter inside of it and compare to all the people living on Earth, that is the comparable weight. So you can imagine that is very heavy, very dense. And under this kind of condition, you will have a lot of strange things happen. For example, there was a lot of strange possibilities. We still don't know what's inside a neutron star. And very importantly, people predict that they maybe can find some free quark inside the neutron star. And so that directly connects to the deepest secrets of our universe. Yeah, so what is inside a neutron star? That is the basic question here. As an astronomer, how can I approach to that problem? Well, if we have an observation, this is the pipeline. If we have an observation, we can measure the mass and the radius of a given neutron star. So I already said neutron star is just a city-sized star. So imagine to measure the mass and the radius of it. So it's very, very precise. I will explain how to do that later. But once we have a mass radius measurement, we can use if we have a construction about neutron star, we can predict it by an equation state, describe it by equation state, and then translate the equation state to a mass radius curve. If the mass radius curve can cross these two measurements, this is a good measurement. This is a good mass radius curve. If not, that is a bad mass radius curve. That's basically the idea to exclude some unrealistic mass radius curve. So mass radius really is the observable. But how we measure that? In 2019, the game changer, we call it Neutron Star Composition Explorer, acronym is NICER. Yeah, well, whatever. That's so. How they measure the neutron stars? Well, it's measure the soft X-ray from the neutron star surface. But why that measurement related to the mass and the radius information? So you can see this video. Basically the neutron star X-ray is come from the hot spot of the neutron star. Then when the hot spot is rotating, when it's come to your eye, you will see a pulse. That is the basic idea. And when the photon come out, it will experiencing some light spinning effect that imprints the space-time information. That is your MR coming. And then it's also related to how to model the hotspot, how the hotspot shape look like. So there was 2 progress, actually. Scientists claim that they found the neutron star hotspots look like a very strange shape. It's an arc-shaped hotspot with another hotspot, and they both located on the north-south hemisphere. And they can really measure the neutron star radius under some 0.1 kilometer. So it's very remarkable. Actually, a lot of people are excited about that, but they still have a lot of things that need to be improved and a lot of caveats about this modeling. First, the systematics come from the hotspot. The way they're modeling the hotspots is actually very random. They use 2 circles to overlap each other. For example, you see the arc-shaped hotspots. That is when you overlap a circle on top of another circle. If you let this circle don't emitting light and this circle emitting light, you will see an arc shape. So this is totally random. And another thing is, actually computation very expensive. Every single computation, because you need to consider a lot of effects, it will take 1 second to do one computation. So it's impossible to test different parameter setting under this kind of regime. So there's a lot of criticism that maybe there is some parameter degeneracy or anything. So my PhD focus, is just to try to improve the hotspots. How to improve that? Well, our idea is maybe we can introduce physics to reduce the randomness. Because we already have a very good model under force-free dynamics to know what the hotspots will look like under a given geometry. But we extended that's a dipole field to all-centered dipole field. So basically, the center of the dipole will be shifted. Yeah, and this is the magnetic field will look like, and this is what off-center dipole will look like. So the basic idea is, given a magnetic field, you can calculate the current density along the field line. Then the current density will define the heating. The heating will define the temperature. This is a simple prescription, and this is the result. If under the dipole field, you can see it's quite non-trivial about the hotspot configuration. It's have a centered hotspots and also have a kind of arced shape. So it's 2 components. And if you shifted it, it will qualitatively different with the centered dipole. We managed to speed it up. Normally, this will need a lot of the force-free dynamics simulation, but we managed to speed it up from a 30 millionth computation to a 60 millisecond computation. And then that's enable us to do the first inference based on this model. This is the proof of concept modeling that we use. We compare our best fits and the data. You can see pretty well. And the hotspots will look like, you cannot see that, but there is a very small, very bright hotspot here, and very large, very faint hotspot there. These two can arguably explain the data itself. Okay, so you can use that to improve your hotspot modeling. Then you will get a better mass radius as promised. You can use the mass radius to model what's inside of neutron star. That is basically another work I've done. I led a collaboration named Compact Objects. I collaborate with several different groups. They're basically more on the nuclear physics part. We put all of the equation states model that's available on the market and test them with all of the observation that we have currently. We already have a lot of the paper come out, but I want to mention this one because we really give the score for each of the model that's available on the market. So basically, it will give a likelihood which one is the best, which one is not. The results, how to interpret that? Well, no any given model is better than another. So every model can explain all of the information, all of the observation. So that is to give you the idea that these kind of experiments or the observation is not tight enough to distinguish any of the models. No matter you want to put dark matter or even the dark energy inside of a neutron star, you cannot distinguish any of the models. They all perform similar. So that's what is the future. What is the future? The future is we want to, that is what I proposed. I want to go here from X-ray to multi-wavelets. Because we know the emission from the neutron star, not only the X-rays come from surface, there is gamma ray come from the current sheet, the radio come from the region a little bit above the polar cap, and X-ray come from surface. We can use this information together to constrain the neutron star interior. We have a good advantage because we try to use GPU acceleration to speed it up. So now, recently, we are writing a new paper that's before this X-ray modeling will take like 5 seconds to do one single modeling from the hotspot to the emission. now we can reduce it to 1 millisecond and very, very robust. Sorry. Okay, so this is the conclusion. Yeah, we will in the future, if we will do multiple astronomical wide survey on difference in neutron stars and give a mass radius constraint of each of them. And we can do also nuclear physics survey on each of the different equation state models. Then we can move the neutron star physics to a process taxable science area, connecting exterior and interior together. Thank you.
John, just looking at the radius mass relation, it always struck me that the radius is independent of mass almost. And what is the underlying physics for the fact that if I change the mass of a neutron star, I don't change the radius? Like, what is the underlying reason for that?
Okay, and that is the degeneracy, you mean?
Well, there must be some physics behind the fact that the radius does not depend on mass.
Oh, you mean when that's increased?
Well, you just plot mass versus radius. And all the data points sit at around 11 kilometers. Between 11 and 11.5, all neutron stars have roughly a radius of 11 kilometers. Why?
It's because of the interaction and also the neutron degeneracy. Degeneracy pressure is different with the. So when you especially for the JW, for the very massive neutron star, you can also imagine that actually the radius of the neutron star should, when it's become more massive, the radius should be decreased, not increase.
Right.
It's because the different behavior compared to the normal matter.
So it's a conspiracy of the physics somehow gives you constant radius. But it is an amazing fact that if someone tells me I saw a neutron star, I can tell the radius is 11 kilometers. I don't care about the mass. Well, that's something to be remembered, right?
Yes.
For fixed equation state.
No, I mean from the data, irrespective of the. I mean somehow can you show us? You didn't show us a plot of mass versus radius from the data. You have that or?
Yeah, well, I can. So roughly the data you can see here. So from the JW30 is 11.6. J0740, this is the 2.1 solar mass neutron star is 11.
It's the same radius.
Yeah, it's almost same radius. That is a very striking result at the very beginning. And people, because it's already excluded a lot of the neutron star equation states. Based on some equation states, it can go this way. Like if you increase the new radius mass, you will decrease the radius. But actually, this but actually this one is like not changing the radius. Even you add too many mass inside of it. So it depends on the equation state models. A lot of the models already be excluded based on the effects.
Right. And the gravitational redshift since the radius is constant, it goes up and up.
Yes.
What is it?
The compactness will increase a lot.
But in those systems, just to be clear, the masses are dynamically measured and the masses are independently, the radii are independently measured. Those are measured values.
Okay, so actually when they measure it, they are measuring the compactness. Compactness is the ratio between M and R, but there will be some independent measurements on mass, so that could decouple this kind of.
Like you have an orbit, like how do you get the mass?
Oh, the mass, yeah. So for the mass, you can have several different ways. A very robust way is use the radio astronomy, use the Chaparral delay. If you're in a binary system, you can measure the mass. But for this one is very remarkable. This one is isolated neutron star. So there is no companion with it. So this is the first time that people infer the both and mass and
the radius is directly measured in some way. It's not from a model. There's no model that's used.
Yeah, this one?
No, the radius you measure from the data.
Yeah. Radius and mass all both from the data, from how you model the emission from the surface. Yeah.
By the way, there is another method which is gravitational redshift. It gives you the ratio of the two.
Yeah.
You didn't mention that, but that's another observable. If you measure a spectral line in X-rays, there was a claim once to detect spectral lines that are redshifted from a neutron star surface, and that will give you the mass of a radius. So that's another method.
I think it's also because the moment of inertia of neutron stars is not yet well established. So there are two variables, mass and radius. So the moment of inertia.
Well, that depends also on the period.
Yeah, sure.
But here, it looks like the radius is fixed, you know.
From what we have measured, actually, can I also ask a question?
Yeah, go ahead.
Great talk, by the way. Talking about the multi-messenger aspect, like, you know, the other way to rule out equation of state is to measure a higher mass of a neutron star from pulsar timing in radio.
Yeah.
So like, I've not kept up with the latest. So what should be the highest mass of neutron star that we should measure to rule out most of these equations of state?
Okay, actually, when people found out the 2.0 solar mass neutron star, actually most robust measurements is about the 2.0 solar mass neutron star. But if you have a higher solar mass, I think most of the equation of state can predict like 2.6, 2.3, something like that. So if you can have something higher than that or comparable, even that 2.6, it will be a very constraining thing. For example, people are arguing that the black widow pulsar, they are saying like 2.3, but with a very large error. That could be very constraining. Yeah, that's another way to do the exclusion, is to do like, if you go higher mass, then definitely you can exclude more. Yeah. Yes.
Any other questions, comments? Yeah, please.
Can you elaborate a little bit about how you reduce the runtime of your, like the first model you were speaking about from 30 seconds, like 30 minutes?
Okay, yeah, we actually use some kind of GPU trick. We just put it on GPU. Yeah, write everything on GPU. That's basically the trick. We eventually managed to try to put everything from the calculating the hotspot to calculating from the hotspots to the light curve. These two processes we all both put on them on a GPU framework to run them, because it's very suitable to do GPU. You are just basically repeating to do a lot of the derivatives or a lot. That is exactly what we expect GPU can get faster. Yeah.
Okay, let's thank Chan again.
Yeah, go for it. Yeah, thank you so much. All right. Hi, everyone. My name is Shoham. Thank you all for being here and having me here. Let me quickly check this. Okay, we're good. So I do computational hydro, and today I'm gonna focus mostly on supernova remnants. So my interest specifically lies in modeling the interaction of supernovae and supernova remnants with their surroundings and figure out clues about the progenitors from these interactions. So starting about type 1a supernovae, these are thermonuclear explosions of carbon, oxygen, white. And as far as the progenitor is concerned, they come in two flavors. You can have a type 1a from a near Chandrasekhar mass white dwarf or a sub Chandrasekhar mass white dwarf. And these are again, different from the observed spectroscopic subclasses of type 1a supernovae. And as of now, there is no clear tie between these progenitor subclasses, which is a physical way of classifying type 1a's, versus spectroscopic subclasses like 91Ts, 91BG lakes, and these are observationally motivated subclasses. So the question I'm gonna try to answer here today is, can we identify the progenitor subclass of at least type 1a supernova remnants, if not for type 1a supernovae? So, okay. So a quick primer on type 1a progenitor subclasses and explosion mechanisms. So when we're thinking about near Chandrasekhar mass white dwarfs, the predominant class of explosion is this delayed detonation model here. So you have a near Chandrasekhar mass white dwarf, and due to the extreme temperature and density at its center, you trigger a nuclear flame, which then subsonically expands. This is called a deflagration, and there's a lot of mixing. The point ashes rise up until at some point it turns into a detonation, which is a supersonically expanding flame front. So the key point here is there's a lot of mixing here till detonation happens, whereas for sub-Chandrasekhar mass progenitors, you have accretion from a companion onto the surface of a sub-Chandrasekhar mass white dwarf. You have this layer of helium that undergoes detonation. The detonation compresses the white dwarf, again triggering a secondary detonation at its center. So these are two detonations. Or you could have white dwarf mergers occurring in a dynamical timescale that also gives you like a detonation-like effect. So the point is there's not a lot of mixing going on in these sub-Chandrasekhar progenitor models. So to sum it up, again, here we have abundance profiles of near Chandrasekhar mass models on the left and sub-Chandrasekhar mass models on the right. So never mind what those are called. So these are more these are double detonations. This is a merger, and these two are delayed detonation models, and this is a deflagration model. The key point again here is there's not a lot of iron. There's not a lot of iron in these near Chandrasekhar mass models because of all the mixing that undergoes during the deflagration phase. In comparison, if you look at the green in the sub-Chandrasekhar models, there's not a lot of iron in the outer layers due to the lack of mixing, and this is going to be our takeaway one. Takeaway two is about the morphology of supernova remnants. So this is shaped in large part by Rayleigh-Taylor instability. So you have an supernova ejecta expanding, decelerating against the ambient medium here. And this contact discontinuity here, that's unstable hydrodynamically. So it gives rise to Rayleigh-Taylor instability, forming these fingers, which are not unlike these broccoli-like substructures we see in Tycho's remnant and in a lot of other remnants. So these things expand from 11 or maybe more kilometers to like few parsecs. So modeling them requires tremendous dynamic range and resolutions. So we handle this using this expanding mesh hydrocode I wrote. It's called Sprout. So the basic idea is that the mesh expands. So it expands with time, which lets me think I need to play this from here. Model model a supernova remnant over large time scales. So you see this super ejecta expanding and Rayleigh-Taylor fingers developing. So how do we analyze this structure? So you take the 3D supernova remnant model. You can see these Rayleigh-Taylor fingers here. So we integrate the density of any given element, or it could be the density overall, in radial lines of sight, according to this here, only in the shocked region though. So you get a spherical map like this, a spherical distribution of the integrated density, and you can see small scale structures here. And the way to identify the size of these small scale structures is to expand them by spherical harmonics. So you get a power spectrum that looks like this. And this is leading to takeaway two. So you have a broken power law shape. It peaks at some wave number, and that's where maximum turbulent power resides. And we're going to call this number L0 henceforth. So you have a broken power law. It peaks at some wave number, which is the scale of these small scale structures you saw on the spherical map. That's the peak of the power spectrum. And this corresponds to the substructures. And here's takeaway two. So the typical size of these substructures is of the order of the density scale height of the ejecta where this mixing occurred. And I'm not trying to make an argument here. This is a statement, and you can refer to these papers for explicit argument. So that's our takeaway two. So for a recap, near Chandrasekhar mass models show a lot of mixing, and iron mixes out to the surface, whereas sub-Chandrasekhar models do not have this. And takeaway number two is the typical size of Rayleigh-Taylor substructures is related to the density scale height of the ejecta where the mixing occurred. So now on to type 1As, you'll notice that these are density profiles. You'll notice that all of them are exponential in nature. So the implication of this is, so the reverse shock moves into the ejecta in a Lagrangian sense at later times. So it encounters shallower and shallower medium at later times. So the density scale height increases with the dynamical age of the remnant. And you can even see this. Okay, I can play the thumb here. You can even see this from this animation again. Well, this is the real model, but I'll jump back. So if you even look at the width of the densities, width of the shock zone, you'll see that it increases, giving us the idea that the density scale height increases with time. Okay, so these are power spectra from these remnant models. This is a time series. So blue is early models, red is later models, and you'll see that the peak of the power spectrum shifts towards the left with time. What that means is, well, to begin with, I'll remind you that the density scale height increases with time. And what this means is that the typical size of your Rayleigh-Taylor substructures with respect to the radius, because this is angular, right? That increases because L is inversely proportional to the size of substructures. So the size of substructures increases with time. And then that tells you that you can estimate the dynamical age of the remnant or even the density scale height just by measuring the size of these substructures, okay? Right, so now on to type 1As. What I'm showing you here are power spectra of different type 1A remnant models at a single instant of time. So again, on the left, you have near Chandrasekhar mass models, on the right, sub-Chandrasekhar mass models, and then green is iron, and the rest are intermediate mass elements, silicon, sulfur. So before even going to the text, do you guys notice any clear difference between the near Chandrasekhar models versus the sub-Chandrasekhar models? I guess that's, well, yeah, I'll jump to it. I hear some murmuring, but I'll just say it out loud. So the power spectrum of the iron distribution, it peaks at a smaller wave number L0 compared to silicon and sulfur, which means iron substructures are bigger in size for sub-Chandrasekhar mass remnants. So we put this in a time series. So this is the ratio of L0 for silicon versus L0 for iron. And you can see that all these models, the sub-Chandra models, they have the increasing value of this L0 ratio, and they settle at roughly 1.5-ish. So those iron substructures are like 40%, 50% bigger than should be in sub-Chandrasekhar mass supernova remnants, whereas in near Chandrasekhar mass remnants, they're almost identical. They should have a similar size. And spoiler, Tycho's remnant is up here, but more about that. So we'll jump to how to measure this for Tycho's remnant. So before we go on, Tycho's remnant is spectroscopically classified as normal type 1A. And to analyze the images, we need to use a technique called delta variance because your Fourier transform doesn't work because you have gaps in the images, the corners, which is a technique I developed in 2024 as a part of my thesis work. So here are these images. And I don't know if I have looked at these for like hours, so it's pretty obvious to me, but I don't know if you can tell, but the iron image and the silicon image, these are different narrow bands. They look different to me. And when you extract a power spectrum out of these, you have a large scale bump because of this arc here. There are of course large scale structures, but there is a change of slope at L0s around like 10, 20-ish. And you'll see that the change of slope, which we associated with this bump in our ideal models with the Rayleigh-Taylor substructure sizes. And those are different for silicon versus iron. So we also match this against our models. These model power spectra were derived from the images as opposed to directly from the 3D models, which is why they also show this bump due to projection effects. But the important point here is the double detonation models match this exactly. The other models do not, the near Chandrasekhar mass ones. And then another step ahead, this time we looked at SNR 0509 minus 67.5, which has been spectroscopically classified as a 1991 T-like. This is an overluminous model, and till date, overluminous subclass. And then till date, no explosion model has satisfactorily described 1991 T-likes. So quickly jump to the image, yikes. So lots of stars in the foreground, which made this difficult. But we were able to extract a power spectrum out of it. And again, we see the same story sort of. So the bend for iron power spectrum doesn't quite line up with the bend in sulfur power spectrum. We couldn't get silicon here. This is optical data, by the way, forbidden lines. And then we could go one step further. We wanted to probe what the helium shell mass would be. I'll quickly skip the future direction, but I'm happy to talk about interaction supernova in general. And I'll leave you with my summary slide. Thank you.
Thank you. We are a little bit over time, but if there are any important questions that anyone would like to ask. If not, thank you so much. That was very informative, all speakers.